here we have a trailer to normal forces because it's important in physics to understand more about normal forces and their geometries. So first, I just want to draw them. If we have something on the ground, a normal force would be perpendicular to the ground, so that would be the normal force. On an incline, this would be the geometry of the normal, perpendicular to the surface. And a wall, that would be the orientation of the normal line. On a curved surface, it's very easy to see what it would be there. Very easy to see what it would be there. Very easy to see what it would be there and there. In other places, we may find it instructive to, at the location, draw a tangent. And the normal then would be perpendicular to that tangent. But really what we want to get at here is that normal forces are perpendicular to the surface, and they do have different orientations, whether they're on a horizontal surface, a vertical surface, something in between, or even on curved surfaces, we can determine the orientation of the normal force by drawing a tangent line. Now, where this is important to us is that when we have inclines or are changing the angle relative to the ground. So just like we had before, we have that normal, and this normal, and this normal. Now, when we did our problem in the last case, we had an object sitting on a flat table. And what was going on is we had our force normal, and it was opposed by the force of gravity, and they were equal and opposite to each other. Now, when we change the angle or the orientation of this, gravity still points toward the center of the Earth. Since Fg equals mg, it only depends on the mass and the acceleration caused by gravity. So Fg is going to be the same irrespective of the orientation of the wall or the surface it's sitting on. So this Fg is oriented exactly the same way as this Fg, and they're the same magnitude. And the same is true over here. This Fg is exactly the same. Now, if you notice, then, if we have an object that's sitting there, we can see that all of the weight is pulling it into the surface. When we are at this orientation, we can see that none of the weight is pulling it into the wall. Here, in the first case, on the ground, gravity is pulling it into the surface. When we set something up on the wall, we just reach over and put it at the wall and let go of it, it falls. Because there is nothing pushing it into the wall. There is no part of gravity pushing the two together. And when we are on the ground, all of gravity is pushing the two together. So what you should probably see at this point is that when it's all, normal and gravity are equal and opposite to each other. And if we look at the case where it's at the wall, the normal force is 0. Because there's no part of gravity pushing it into the wall. There is no need. There is no need for the electrons here to be repelling or supporting each other because they're not being pushed together at all. So what that means is if we go from a maximum of Fg at a horizontal surface, our maximum, and we have a minimum equal to 0, our maximum equal to Fg, then you could see then that there's some, as gravity is acting on this body here on this inclined plane, it is only partly pushing into the surface. And you know if this surface is slippery enough when you let go of it, Not only will it stay on this surface because gravity is pulling it downward, pulling it into the surface, it's going to pull it down as well. So some part of gravity is pulling it into the surface, perpendicular along the normal, and some of it is pulling it down the plane. But the point we want to get at is, when it's horizontal, the normal force is equal to the force of gravity.